two. So and if you recall, the way we began all this, the Walsh functions, is we did all this lovely Wavelet theory and the multi-resolution analysis. And then we said, well, we have to complete the tree. So we did Wavelet packets, which the way I did it was very, very technical. You don't have to be quite as technical in some presentations, but I really like how constructive it is the way we did it. So Wavelet packets. And then we took a very fundamental example, the Haar MRA. And we found out that the corresponding Wavelet packets are the Walsh functions. So, in fact, that covers a lot of ground, both historically and just technically what we did. And it's sort of dramatic, I think. It's, because the Haar system began in 1909. Walsh did his fundamental paper, Walsh functions, in 1923. There were the Franklin systems from the 20s, and that, along with the Haars, eventually led Stromberg into the sort of immediately intellectual predecessors of Wavelet theory. And in the meantime, Walsh functions, because of the way they were constructed by Walsh, but they turned out to other constructions, became useful in technology after World War II. And of course, Wavelet theory tied in with basic developments in speech processing and image processing, with coding theory and image processing. And so it really was a fantastic intellectual journey. And so we reached the stage where we began with something not so general, but rather mathematical, and we were writing down very specific functions. So I want to carry this through because it leads in another very beautiful direction. So let me recall for you the definition of Walsh functions. And there are several equivalent definitions, and they all come down to, you don't have to photograph this, they all come down to, there are three different definitions, and one of them looks apparently quite different, but they come down to just renumbering of the same set of functions. So I'm just going to briefly go over this material because we already did it, but just because we haven't seen each other for 2 weeks. So we're going to have the Rademacher functions. Someone shut that door, please. Rn n equals 1, etc. And these are the Rademachers. Did his work about the same time as Walsh. And I've mentioned before that Walsh was professor both at Harvard University and the University of Maryland. Very outstanding analyst, and he only wrote this one paper in what now called Walsh functions, but these functions have had a major impact. So I'm going to look at the Rademachers on T, on the course, and they're defined in the following way. For all n equals 1, etc., sine of 2 to the n it. And two things to recall. That if we look at just the ordinary signs, but for every integer, so a sequence square root of 2 sine of pi n t from n equals 1 to infinity is an orthogonal basis for L2 of the torus of 0, 1. And the other thing we want to recall is that the Rademachers are orthogonal, but they don't form a basis. They're R n is orthonormal, but not an orthonormal basis for L2 of the torus, and this elementary calculation we did last time. And of course, the way the Rademachers are formed is rather simple. One begins with the half function. So we're on 0 to 1. And we just have this function like that. So that's R1. And then R2, R3, R4 just squeezes it halfway over and adds it to itself. So in particular, R2 is goes to 1, there's a half, and we're at 1, pretty straight. Okay, and et cetera, et cetera. So, so in particular, R3 will have 2 to the n cycles. This has 1 cycle, this has 2 cycles, and it goes up by powers of 2. And then Paley is the one who knew of Walsh's construction, which was quite different than what Paley wrote down. But Paley provided the following description of Walsh functions, which I guess I like the best as far as getting started in the subject. And it ties in very neatly with this beautiful piece of mathematics. So the definition, sequence of Walsh functions, how did I write it there? N equals 0, 1, defined by W, 0 is identically 1, and for all n equals 1, 2, etc., W n of t is equal to the product of the Rademachers Rj of t, where epsilon j is equal to 1. And that epsilon j is just when we write out what n is. So we have where n is equal to the sum of the epsilon j's 2 to the j minus 1. J equals 1 to infinity. I'm just writing out its dyadic expansion, the binary expansion. And here in this product, I'm just, of course, this is only really a finite sum, and I'm just looking at the j's, which epsilon j is equal to 1. Okay, so we did all that last time, and we noted that, that W of 2 to the J minus 1 is equal to R to the J, R subject. So basically, the R's really are going out diagonally. You can see that you can piece them together in a certain way. And we, of course, drew a lot of those functions. So we had, in particular, W0. W0 is identically 1. But W1 is going to be the same as R1. And W2 is going to be the same as R2. And then we get a change. W3, because of the dyadic expansion, is actually going to be equal to R1, R2. And what does that look like? Well, that looks like this. Go to 1, and we come down as a half, a fourth, and a fourth, so we come down like that. Okay. And I talked quite a bit about these things last time. Now, let's see. So I mentioned moments ago, but let me repeat that Walsh came up with his functions in 23, that Paley in the early 30s did it this way. Walsh's definition is recursive, probably can still be used, even though it's a very purely classical mathematical paper. And this, of course, is not recursive. But the only differences between those two and what's later called the Walsh-Kachmach functions, they're all the same except on how you count them and how you list them. And I guess I'm not going to do anything about that. Okay, well, basically, we're going to be looking at something that's, and the reason I want to continue with the Walsh is something that's rather dramatic mathematically. In order to do it, I want to do a little bit of Fourier analysis on finite abelian groups. Because the kicker, nobody's keeping secrets, is that we're going to look at a certain totally disconnected group, very, very constructive, so even though that sounds fancy. And we're going to look at its dual group, which I'll define, and they are going to be the Walsh functions. It's really spectacular, to my way of thinking. And then we'll proceed with Wavelet theory in higher dimensions. So the first, let's do that today. Well, a long time ago, in a faraway place, Gauss proved the following theorem. In the following way, and he didn't have this terminology, but knew how to do it. Let G be a finite abelian, that means commutative, group. Then G is isomorphic. That's the same as a nice bijective homomorphism from G onto the following thing here, to the following. A direct product N1 with N2 with N, where each Nj is of the form Pj to the Nj not all algebra books have this proof in there, but a lot of them do. And I'm basically not apologetic about stating this in the MAIT class because basically, if you look at many of the theoretical engineering journals nowadays, some of them are very, very mathematical. And even dealing with finite abelian groups now, people deal with that they don't have to be abelian. They use them in the construction of codes and the like. So this is, it is 200 years old. Okay. Now, let's let. No, they can repeat themselves. Right. Yeah, it's a great theorem, and and we're going to be looking at. Question time? We're going to be looking at groups like this in order to build up another group whose dual are the Walsh functions, which are functions that are very, very. Anyhow, first of all, the characters of G are the homomorphisms E from G into C, such that for all G in G, the absolute value of E of G is equal to 1. And I'm going to write the homomorphisms with multiplication here in C. So, and E of G1 plus G2. So I'm having addition, that's just a formula. Addition in G, the multiplication in G being addition. But I'm going to look at these as products. So those are called characters. And basically, with abelian groups, and this is a sloppy comment, but it can be quantified. With abelian groups, there are lots of characters, and you can do a lot of analysis because of that. When groups are non-abelian, like matrix groups, so I mean, basically groups arise very naturally, especially now that we have MATLAB. You just don't have enough characters, and that's one of the reasons we have representation theory. One looks at representations of the groups. Okay, so given that situation, we have the following theorem. So the characters of G, so the character, so G hat is the character group. And it's a group because you can essentially do the same thing as you have here. You have E1 plus E2 operating on G. It's just going to be E1 of G, E2 of G. So we're going to denote the set of characters this way, and then it turns out there's a nice equivalence isomorphism that says that G hat is equal to G. Now, for the case of the real line, if I looked at the characters of the real line, we have the same property. But if I look at, if the group were the integers, the character group is the torus. So things become interesting. Okay, so let's say a few things about finite abelian groups. Definition. the discrete Fourier transform of x from G into C. Now we've already talked about the discrete Fourier transform of Zn, but now I'm just taking any old finite abelian group. Now, in theory, because of Gauss's theorem, we can make very messy proofs in the direct product, but that's sort of ugly, and you can get just caught up in the awful notation, and then you get pulled down by it. So it turns out you can prove all these things in a much more in slicker, more understandable ways. If you just think of a finite abelian group generally, as opposed to that characterization for many cases. That characterization is very nice for certain things, obviously. So the DFT of x is defined as for every E in G hat, x hat operating on E is the sum where G is in the group X of the group element, and then E of the group element. And that's exactly what the DFT is in the case of the finite group Zn, where that's n integers, the modulo arithmetic. And the following is an inner product, just as we have for Hilbert spaces, but just looking at things on finite groups, on L2 of G. G is just a finite group. So that is to say we've got X, Y, where X and Y are in L2 of G. Is just going to be defined as the sum X of G, Y of G conjugate as G runs through.
I'm not sure I understand the definition.
Okay, just go ahead.
So you're picking an x from your character group, and then
No, I'm taking a function on the group.
Mm-hmm.
So now I'm taking a function, any old function.
I got it.
And so I can say this the way, since that's just a finite group, we can write x belongs to L2 of G with counting measure. So in this case it's L2 of G, and it's just all the it's what it is. In the case of the finite group, it's to the extent I define anything so far, I'm looking at any function from that group. Any function. Okay. I can call it L2 of G, or I can call it LP of G, or I can call it tiddlywinks. But we're just looking at the space of all functions on the group. And we can now talk about its Fourier transform. DFT x hat is defined on, now it's defined on the group. And the way to think of it is in terms of the usual DFT, because that'll be very illuminating. I mean, if you take Zn equal to G, then if you take function x from Zn into C, any old function, then how do you define the DFT? The DFT which is what you do in your computer, is x hat of x is x hat at n from the previous result, we know this is, we can think of this in terms of Zn hat, but this is just the definition for all n and Zn. This is equal to the sum, m equal to 0 up to n minus 1, okay, of x m e to the minus 2 I mn over n. That's the usual DFT. And all we've done here is note that the characters of, Zn hat turns out as Zn, and that equivalence to make that Zn the character group brings in the exponential. So this we put on a computer. Well, because of Gauss's theorem, this definition here also goes in a computer. Not parallel processing, but maybe product processing computer. Actually, non-jump. What's that?
Yeah, so you think of the Fourier transform as like an array for all E and
Well, hey, the Fourier transform is a function, so I have to define it at points. So I'm defining the points I'm defining it at are the characters.
Okay.
And that's exactly what we're doing here, because this Zn here, even though it's the same notation, even though we don't tell people that when we first teach them the DFT, it really is the character group of that. Okay. Now, some other things we want to say is the, let me just, some of these calculations are not entirely obvious, but they're all sort of doable. Let me list a couple of facts. Fact A, G hat has the following properties. For all E1, E2 up. Obviously, people are doing your projects. We're not going to give you more exercises, but this is in the realm of exercise. By the way, I think some of the topics you've chosen as projects are very, very good. I'm looking forward to reading your papers. E1, E2, that inner product, where I can think of these are functions on G, so I can talk about them in the same way I talked about an inner product here. This is equal to 0 if E1 is not equal to E2, and it's equal to the cardinality of G if E1 is equal. Now, if you remember, there's a song that goes like that. If you remember when we proved the major thing about this DFT, the classical DFT, is the inversion formula, the major first result. And that says that if you're given x, and you compute x hat, then you can rewrite x in terms of x hat. So you're just going to have x there, you're going to have x hat here, and you're going to have 1 over capital N. But in order to prove that result, it's very elementary. For the case of the exponentials, we used a geometric series argument. You can't quite do that here. But what you can do is do the following. And where you need that is right here. If you want to prove the inversion formula, this is an essential part of the inversion formula, even for this one. And so, but I don't have the geometric series formula here, raising things to powers per se. So let me just make a little note that you can think about after class, that the proof of this fact for exponentials involves the geometric series. In this case, I don't have access to that, so how would you prove it? And in this generality, oops, we can compute that E, that for all G in G, E1 of G, E1, E2 is equal to E2 of G, E1, E2. And if you can do that, then if E1, E2 is not 0, I mean, you can get the result from just those facts. But anyhow, so there's a calculation that involves this. The second fact I want to mention is that fact B, given G1, G2 in G. By the way, for the sake of, if you're interested in the subject, I mean, it really is a very useful subject. There's a beautiful book on finite, I can't remember the title of the name, but it's by Audrey Terrace. So if you look up her name, you'll see the book. It's a beautiful book on the subject that she wrote a number of years ago. And now in our series, we're also coming up with a book on the subject. And these fellows are much more engineering oriented than Audrey is. So I mean, the subject does have genuine applications. Anyhow, the second fact is, given G1 and G2 and G, then the sum over all the characters in G hat of E of G1, E of G2 conjugate, that's going to be equal to 0 if G1 is not equal to G2, sorry, and it's going to be equal to the cardinality of G hat if G1 is equal to G2. Okay, with those two facts now, we can get Fourier analysis in the following sense. So with these two facts, we have the following. Okay, everyone has this. It's Monday, next Monday, okay? And it's in 1310. So theorem. Inversion and Plancherel. So for inversion, it's exactly the inversion formula that we had for the classical DFT, namely for every x in little L2 of G, or whatever space you want to call it, we're looking at any function on G. And for all G in capital G, x of G is equal to 1 over the cardinality of G hat, and then the sum over all E's in G hat x hat of e, e of g. Okay, so exactly the same formula as for the classical DFT. And then the Plancherel theorem says that for every x in L2 of G, the norm of x, which we define this way as the sum x of G quantity squared, where G is in G, and we take it as 1/2, that guy is equal to 1 over the square root of the cardinality of G hat, and then the sum of x hat of E, quantity squared, all to the 1/2, where E runs through. Okay, so the proof of A, these proofs are amusing, so let me do it. Unless I get bogged down real quick. So proof of A, if we look at just the right-hand side, we're going to have that the sum x hat, and I'm going to pick a particular G naught since I need to use arbitrary G, at E of G naught. Okay, so that's the right-hand side without putting the cardinality condition in, where E runs through G hat. And now I'm just going to write out what x hat of E is. So this is the sum E and G hat, and then the sum G in G of x. So x hat of E is x of G, E of G conjugate, E of G0. Right? And then I'll just bring out the sum over the e's that I can. This is equal to the sum over the e's in G hat of E of G0 times the sum of G and G x of G, E of G conjugate. And now, I guess I should have switched. So let me switch. I'm sorry. So this is equal to, I didn't make a mistake. I just being redundant. This is equal to the sum over G in G of x of G, and then I want to have the sum E in G hat of E of G0, E of G hat. And now I can use my guy over here, fact B. And so this is equal to, by fact B, I'm going to get the cardinality of G, the fact A, doesn't matter. Cardinality of G, x of G0. Okay, so basically, that's how you do it. Now, part B is a little trickier. I think I want to do it in any case. How's my time? Oh, yeah. So for part B, have that by definition, the norm of x, the way we defined it over there, is the sum of x of g squared, etc. So x of g, I'm going to put in the inversion formula that we just proved. So this is equal to 1 over the cardinality of g hat, and then the sum over g in g. And now instead of just putting in the definition, I'm going to put in what the x of g is. So I have this guy here, which is the sum, putting down the inversion formula, x hat of e of g, quantity squared, as I sum over e and g hat, all to the 1/2. And then if you just write that out, because I'm going to just write out the square, I get 1 over the cardinality of g hat, and then the sum over g in group. And I'm going to have the sum over e in g hat, that's the sum over, I'll call them e primes in g hat. And I've got x hat e of g, x hat e prime of g, all to the 1/2. Right? And now these are all finite sums. I'm going to bring in and just sum over the g's. So this is 1 over the cardinality of g hat, and then I'm going to have the sum over e, the sum over e prime, and then what do I have? I've got x hat of e, x hat of e prime, and then I've got the sum over g's of e of g, e prime of g. I omitted a conjugate here. Like so. Okay? And that's just equal to, because of the these facts here about the 0 and 1, which I should have done in terms of the dual group, but I didn't. But this is then equal to 1 over the cardinality of g hat, and then the sum over e in g hat of the cardinality of g, x hat of e quantity squared. And that's all to the 1/2. And that should be it. Yeah, that's the right hand side. Okay, so basically it's, once you have these two little facts here, you have the Taschereau and the inversion.
What has one of the square root of it?
Oh, I should have had the,
Just factor it out.
just factor it out, and then I've got the square root
Oh,
Yeah.
oh.
in those
I
cardinality.
didn't see the one inside there.
Yeah. Okay, so basically, it's the elementary theory, but we just did discrete Fourier transforms for finite groups and did not omit too many details. There's also a Poisson summation formula that is the same proof as the one we gave in class, as far as the formal symbol pushing goes. And basically, Boston summation form, except that we don't have to worry about anything about convergence, finite groups, Boston summation formula. And this is certainly a theorem. If you take x in L2 of G, then, and you take H contained in G, a subgroup, and then you look at the group GH. That's a group. It's a finite group, so you can talk about its character group. So with that notation, we have the sum x of h in the group H is actually equal to the sum x hat of E in the group G H hat. Okay, now this is exactly what our Poisson summation formula says on the real line. Because what we do is we take the discrete group Z. So suppose G is the real line. Then we take the discrete subgroup Z. And I've got a function which is defined on the real line, assuming it's continuous and L1 and all that sort of stuff. And its Fourier transform is continuous and has some other maybe decay properties, which we don't have to worry about here. Then that's what the left-hand side is. Well, the right-hand side is what? Well, if I take R mod Z, that's the torus. If I take the hat of that, that turns out to be the integers again. And so I'm really looking at the sum of the Fourier transform of the integers. So this is exactly the formula, the Poisson summation formula that we have in the real line. Only now we write it down for finite groups. Okay. Let's see where I am here. Now, one of the things I want to mention is an example. ZP P prime is a field. We can divide it. Okay? And if n is not prime, Zn is not even an integral domain. Zn is not a field, but it is a commutative ring. Now, I must say, I'm interested in this because of what I want to say about the Walsh function, but today. But you may recall when we were talking about codes, if you wanted to write down these Kazak codes, as to say unimodular functions defined on Zn. So you have a function defined on Zn into Z, its absolute value is 1. And then its autocorrelation is 0 every place except at the origin. And you can imagine why that's useful in communications, to have two separate signals not knocking each other out and being able, one signal carrying one message and one signal carrying the other, and then one signal is the other signal's noise, so they block each other out and all the good things happen. But if you want to define these, a lot of these codes, if you do it on ZP, where P is prime, there are only finitely many really different ones. If you look at Zn, where n has squares in it, like Z4 or Z9, then there are infinitely many of those codes. So depending on your interest, what I just said, by the way, is not easy to prove. But that sort of thing is, that's one of the reasons these things arise in applications. It's not just, has to be in a number theorist's play box. Okay, now, let's move to the next step here. The next step is we're going to come down to Walsh's, but I actually have to do something a little fancy before I can get to the Walsh's. And it actually is essential. So we talked about characters on finite groups. Why not take the extra step and let G be a locally, now there may be one or two engineers in the audience who don't know what I'm talking about here, but roll with the punch for a little bit because it's all going to come together as far as the when we talk about the Walsh functions. But let G be a locally compact abelian group. So that means it's a commutative group. It has a topology, which I want it to be Hausdorff. It's going to separate points in a nice way. It's a group, it's locally compact, it separates them in a very good way. And it's going to have a basis of a neighborhood system of compact sets for every point. If you don't know what that means, just think of the real line. That's a locally compact abelian group. Now there are people who have religion about this, and in any religion you have to have good hymns. And so the religion here is that the music is very appropriate if you use Gregorian chant. The G be a locally compact abelian group. You know, you get the image. All the monks. Anyhow, let G be a locally compact abelian group. And we want under which the mapping G cross G into G, where a pair XY will go into X minus Y, is continuous. Okay, so these are groups, they have a topology. Like I'm just defining this mapping here, and I want it to be continuous. Okay. G hat, the characters on G is the set of continuous homomorphisms. Same as before, only now I need continuities. I had continuity automatically with the discrete case. Continuous homomorphisms gamma from G into C, such that for all G in G, or X, there's usually X is there. For all X in G, gamma of X in absolute value is equal to 1. And again, I want to look at this additively, and I want to look at this as multiplicative. So I really have gamma of X plus Y we're going to write down is gamma of x. Gamma. And so it's an amazing thing. If you just play this game and for say like the real line, and if you look at L1 of the real line, then for those of you who've taken real variables, you know that the dual space of L1 of the real line is L infinity of the real line. Well, basically, if you look at all, and those are the continuous linear functionals on L1. But now, what if you look at the continuous linear homomorphisms on L1, taking values like this? Those turn out to be the exponentials. Imagine, e to the 2 pi i's. And so, if you take an algebra and a convolution like L1 on the real line, so this is an object you know, and you look at its continuous homomorphisms, you get the exponentials. So, in that sense, the algebra L1 leads automatically to the Fourier transform. If you played that same game on a different algebra, let's say I'm saying stuff that may be a little advanced right now, but it's okay, for perspective. If you take a different algebra, like distributions with compact support, that's an algebra under the same sort of thing, then its homomorphisms are going to also be exponentials, but it'll perform e to the zt, where z is a complex number. And so that leads to the Laplace transform. So there's a folklore here that says that you take an algebra, take continuous homomorphisms, you're going to get a different transform. Okay, so basically, well, that's one of the reasons characters are interesting. Okie dokie. Now, with the finite groups, we had the g hat is equal to g. That's not the case for necessarily for arbitrary locally compacted Viennese groups. But I'm not going to prove anything at all, but I'm just going to say that fact is a natural topology to put on g hat, and then g hat fat is equal to g. Okay. Now, let's zero in on the Walshes.
That's for any locally compact abelian group?
Yes.
Okay.
I mean, basically you put what's called the compact open topology on G hat. You've got a topology here. There's a natural topology to put on this space, and it becomes locally compact again. And it becomes a group, which you can define a group action as we did there in the dual group. And it turns out then you can talk about the characters on here. Well, the characters on here turn out to be G itself. Without the abelianness, you don't have any of this holiness. And of course, life gets very exciting in its own way because representation theory then becomes a sine qua non. Okay, so now let's look at a very particular example. Let's look at Wn, and let's just take Z2 cross Z2 cross Z2 n times. Now, I'm not going to do that do the following in this course, but basically I'm doing a little bit of harmonic analysis on Z, because it really came from the MRA. This is the amazing thing. And it goes full cycle, which I'll also mention at the end. But Z2 here is just, each Z2 is just the group consisting of, the additive group consisting of the numbers 0 and 1. 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 1 is 0. But there's also a whole other type of analysis called p-adic analysis, where you're going to look at things called Z2 or ZP, and these are p-adic numbers. In this case, p-adic integers. And basically, they sometimes use the same notation. If I was really being honest, but I don't have to be here since I'm only going with Z2, I would write here Z mod 2Z if I was comparing myself to the p-adics, but we're not. And by the way, I have no idea about this, but one of my kids and I wrote a paper on p-adic wavelet theory, and which I thought was just for mathematical fun. And there are people in quantum mechanics interested in this subject. I have no idea why. Maybe they're masochists or they want to make us feel good. Anyhow. Okay, Zn, and this is n times. And W stands for Walsh in this case. Although he doesn't have a claim to it, we're going to end up with a dyadic group, which is. So we're going to look at a mapping, which I'm going to call iota, from Wn into 0, 1, 2, all the way up to 2 to the n minus 1. And just for the heck of it, we'll call this Q. Yeah, I am making it worse. Okay, we won't call it anything. We don't have to call it. So what we're going to have here is, if I take an element in this n, it's going to be a sequence x of epsilon 1, epsilon n, where epsilons are either 0 or 1. And it's going to go into the sum epsilon j 2 to the j minus 1. J equals 1. Okay, so what we have here is, this is a bijection. This is iotas of bijection. Now, Wn is a group, component-wise addition. Now, this is actually a big, big distinction between this direct product and what one does in the p-adics, in case anyone's interested in the p-adics. In the p-adics, you carry. Here, we don't carry. We keep the group operations the same. Right, we stay in each coordinate of the group. Now, since this is a group, I can talk about iota. I can transfer the group operation here into a group operation here. And I was going to do the calculation for you, I did it out. But a natural question to ask is, I mean, this, after all, you can think of, if you wanted to, as Z 2 to the n, which has addition mod 2 to the n. So does that is that a homomorphism? And the answer is no. So basically, iota carries the group operation from Wn to Qn. But the group operation in Qn is not addition mod So there's algebra you can do there if you wanted to. Now, the next step is, we're almost there. Talking about how the Walshes arise. The next step is to look at the, consider the complete direct sum Z2, a countable collection of Z2s. And by this, what I mean is, I'm looking at the direct product. This is a countable direct product of the Z2s with component-wise addition. Yeah, don't carry. And we're going to call that direct product D, Math Blackboard D, where D is for dyadic. D is also, well, I'll tell you, D is for dyadic. Now, let's put the product topology on D. Let's put the product topology on D. And what that means is I'm going to look at open sets where, I mean, these are just 2-point components. And so basically I'm going to take, I mean, the product topology you learn in topology is you take a finite number of open sets for some of the components, and then all the rest of them are the whole group, are each of the complete components. But here, that means I could have, it makes it look simpler anyhow. I could have a set consisting of 0, set consisting of 1, or the whole set. But, so without going into a lot of detail about that, I just said it all. I can't say much more. Let's put the product topology on so Z2 is endowed with the discrete topology and D is then given the product topology. Well, as such, my Tikhonov's theorem equivalent to the action of choice. I suppose everything's equivalent to everything else. I mean, you and I are equivalent to do the proof the right way, but you can actually prove. Do I want to be equivalent to you? You don't want to be equivalent to me. All that old age. And anyhow.
Reminds me of a joke kind of a story Richard Feynman told in one of his books. Some physicist came running up to him and says, Richard, I figured out why all the electrons have the same charge and the same mass. It's because they're all the same electron. But Maybe if you have to be a physicist, I don't know.
That's wrong, they're all Fermi, Fermi.
They're all what?
They are all Fermi particles.
So much for your joke, Brent.
I didn't hear that. They're all what?
Joke, man.
They're all,
Overthinking it.
anyhow, the antithesis of that, of course, is when Anna Pavlova said to Bertrand Russell, we should get married, just think with my good looks and your brains, just what the children would be like. And he said, yeah, but what if it's my good looks and your brains? I think that might have been very insulting to her. She might have been brilliant for all I know.
Couldn't reel himself down.
He couldn't settle that? He certainly
Couldn't
couldn't.
get his reputation.
Yes, he did. And if you ever saw him, you wonder how he got it. Okay, what are we doing here? We put the product topology on the dyadic group. Now, as such, because of the Tikhonov theorem, V is a compact abelian group. Turns out it's even more or worse than that. It's totally disconnected. It's like some people. The is also totally. That's a technical term, I suppose you might not have heard it. Disconnected. That is no component, connected component. Contains more than one point. Okay. That's actually remarkable because we're aiming for Walsh's here. What does that do for Walsh's? So, a few calculations, and what I'm doing right now is wondering how much detail I should go into here. So it's also called the D is, because of this fact, D is also called the Cantor group. Not because Cantor was totally disconnected, even though he did have psychological problems, because the Cantor set is totally disconnected. Okay, and I'm just about deciding that I'm not going to do some of these details. I'm perhaps fishing out too much of this right now. And so I think I will go right to the heart of the matter. So what we have is we've got a group that's compact, it's totally disconnected. And the amazing fact is, it was observed by the theorem, we would find D hat is equivalent to the set of Walsh functions on and basically, I mean, this is just Z2s here. this is dramatic actually to me. It's been around for a long time too. It's basically around the same time the Russian Malenkin thought of the natural thing to do to generalize this from Z2, and so the whole theory built up at this more general level, and you're talking about totally disconnected compact groups, and basically tremendous amount of analysis is done in these groups because, as we mentioned earlier in the course when I was talking about Haar series and Walsh series, sometimes the Fourier analysis in those series is a lot simpler. And I said I was going to come full circle around, and things like distribution theory and all these other subjects, HP theory, are all done on these groups. And in practice, when I was sort of coming up in harmonic analysis, the sort of harmonic analysis we would do sometimes the proofs would be easier to do on these groups, and then you just transform them into Euclidean space where things were in theory more complicated. Okay, so now let's look at a couple of things here. I just said it's totally disconnected, but on the other hand, we can do the following, and this is one of the ways the mapping is made to talk about the Walshes. Consider the mapping. Consider the mapping, I don't know, theta, from D into 0, 1. And what we're going to have here is we're going to have a sequence of epsilon j's. J equals 1 to infinity. Epsilon j's are just zeros or ones. And now instead of going here as we did with Qn, we're going to take it into 0, 1. So we're going to go into the sum of the epsilon j's 2 to the minus j. Well, that's a nice mapping, and it's essentially onto. It's not, things aren't perfect because for rational numbers, or some rational numbers, you're going to get 2 binary expansions. But it's just, you can mod those out because it's just going to be a set of measure zeros, those rationals. For the irrationals, it's a unique representation. And so we've got a surjection up to a set of measure 0. And so that means we can transform things back and forth. And D has an invariant higher measure on it, as does every locally compact group. And it turns out phi induces a mapping from that higher measure onto a vague measure. There are lots of details to be proved here. None of them is difficult, but I just want to tell you the big picture now since I'm seeing I spent more time on this than I wanted to. Phi is measurable. As to say, maps measurable sets on the measurable sets, and maps our measure mu on G to the vague measure. On 0, 1, okay? Definitely details to be filled in there, and definitely not beyond you. And now, with that, we can do the following. For each n, there exists a unique gamma n in d hat, such that that is non-trivial only on the nth factor. That is gamma n of some sequence epsilon j of zeros and ones is actually equal to -1 to the epsilon n. That's how you define it. Now, what transpires is that, repeating this theorem, d hat, I'm going to now call it W for Walsh, is the set of finite products of the gamma n together with gamma 0 identically 1. And this is exactly the analog of the Walsh functions, and the gamma n's are going to correspond. You can see you're going to make them up in terms of the Rademachers. Now, I'm not showing you those step functions, but the way one can show the step functions is one can define on D essentially dyadic intervals, certain sets in D, so the capital phi actually takes it on onto intervals of 0, 1. So that's how it's done. It's I think, extraordinarily beautiful. There you go. Let me,
I have a quick question.
of course, Brian.
I'm thinking of the topology you've defined over there.
The product topology in D?
Yeah.
Yeah.
And that seems to me, when you translate in terms of that mapping, does that mean the open sets are all like step functions? Does that make sense?
Well, the open and closed sets are the same.
Okay, so the clopens, or whatever you're going to call them,
Okay.
are they little?
If you want to call them that.
Okay.
I know there are some people who do.
They're like step functions, right?
Yeah, and basically, that's how you get that's one of the ways of proving it's totally disconnected.
And I'm wondering, does that relate? It seems it heads straight into like the Haar functions.
Oh yeah.
Is there-
I mean,
is that
it's definitely.
That's the relation between the topology there. Okay.
And the only question is, which I want to address in just a second. Well, there are a couple of questions, but I said it was totally disconnected, and it is because when I define these sets on D, there are these dyadic intervals. They turn out to be open and closed in D. I'm just repeating myself. But it's a little bit more dramatic than that, in the sense that one can write, let's go over here and just write it down, and maybe I'll stop. The fact, the mapping D into C, the triadic Cantor set, that takes an element of D, which is just zeros and ones, into 2 times the sum of epsilon j 3 to the minus j equals 1 to infinity. I might have to take a j minus 1 here. I wasn't thinking of that. I can't think of my feet right now. So, but that mapping is a homomorphism. So the mapping with the topologies on D and C, the one in C induced from on R, that mapping is a homomorphism. So, I mean, the proof is essentially the way I just said it. You have to find these dyadic intervals on D and see how they transform. But it's beautifully stated this way. And I guess just to summarize, we can put it, I'll just put it right here. So the last thing I'll say, and then we'll take a break. In general, let G be a compact abelian group. For example, the torus or the Cantor group. G hat. Now, these are functions on G, so they can be considered as elements of L2 of G. G hat form is an orthonormal basis for L2 of G with normalized time measuring. And so basically this thing all ties together. We formed the dyadic group. We sort of saw, even though I didn't push the details through because I didn't define dyadic intervals carefully enough. And I was planning to, but I also don't want to gain too much animosity. Those dyadic intervals, when you translate them under our mapping phi, are really going to allow you to go in and make the Walsh functions look like they're supposed to look. But this is the way it works with the gamma ends, finite products of the gamma ends. And those guys, since they're characters, whoops, D hat. Those guys, since they're the characters, they are an orthonormal basis. I mean, this is a general theorem. The characters form an orthonormal basis for L2. Now, if you forget the dyadic group right now, and you just look at T, the torus, that's just saying that the exponentials, e to the 2 pi I n gamma, form an orthonormal basis for L2 of the torus. But this is just a general fact for any compact abelian. So, I guess for the last hour and a half, I've been trying to paint a pretty picture. I may not have done it too eloquently, but just to summarize before we take a break, we began this whole business by doing MRAs. We felt compelled to complete the trees, and we did it in a there are other ways of doing it. We did, I think, a very beautiful way with the theory of wavelet packets. We saw that one of the most basic examples we have, namely the Haar wavelets, when you complete the tree, give rise to these functions which turn out to be exactly the same as the Walsh functions that Walsh did in 1923. And then the Walsh functions themselves, we could have just stopped there, because a bunch of step functions is formed off a normal basis. But all of a sudden, if you start thinking in terms of these groups, you see that they are tied together with this very famous dyadic group, and in the sense that the dual group of the dyadic group are the Walsh functions. And there's a tremendous amount of business going on in this area. I think with that, let's take a break.